Good morning, chemists. Welcome back to Quantum Principles, Chemistry 132B. And this is going to be lecture number 8. And I'd like to start by saying that next week at this time, we will have our first quiz, in-class quiz. Some people call it midterm, some people call it test, but it is all of those things, basically. It's just doing a couple of problems, and we do that in Canvas during the regular lecture time. Okay, so what does that entail? It means that instead of attending the lecture at this time, you go to your Canvas website and select a quiz that is due for that day. Okay, so we'll have, it's going to be very clear in Canvas. There's going to be a midterm quiz. Number 1, you select that one, and then you start doing it at 10 o'clock in the morning on Friday, and it will close 50 minutes later, 50 minutes later. We are probably going to use Respondus browser. I'm not sure yet. I have to kind of like figure that out. It is going to be open book, okay? So you can use any written or printed information. What we will do probably if we are going to use a lockdown browser is to just prevent you from using internet tools for looking up answers and communicating with your buddies. That's something we don't like you to do. You should have all the information available to you to solve the problems. And so therefore you can use printed materials. You just shouldn't communicate with your peers, okay? So that's basically how we're gonna run it. So you are a little bit on your own. You have to be able to remember that you should do that on Friday. And I will give you reminders, written reminders and verbal reminders, so that you can start at 10 o'clock in the morning and do the quiz on time and finish on time. So it's about a 50-minute slot for people who need more time and have requested that through the DSC. We will grant that as well. So they will have a little bit more time to complete the test. You don't probably need the full time slot because the quiz is short enough to complete it well before the 50 minutes that is allocated to it. So you should be in good shape. If you're comfortable with the material, then you have nothing to fear, and you will be doing very well. This is just how it is. So make sure that you feel comfortable with the material, you feel like you have a good handle on it, and then you should be ready to go. Again, I'll give you reminders and we'll talk about it. What kind of questions they are. Indeed, they are looking very similar to the homework questions that you guys have been doing so far. So something of that kind, in addition to some conceptual questions. Most of them are going to be multiple choice, not all of them, but that's what you can expect. So the material for the midterm quiz, midterm quiz is lectures 1 to 10. Okay, so this is lecture 8. So this is going to be part of it, as is Monday's and Wednesday's lecture next week. It's going to be part of it. Okay, so again, I'll remind you of that. And so I would recommend you to look at your lecture notes, make sure you understand what is being communicated there. And of course, the homework questions you guys have been doing, as well as the worksheets, are very representative of the kind of questions you may expect. Okay, so hopefully that's clear. And we will again say more about it on Monday and Wednesday, just to make sure that everybody understands. All right, so with that said, let me dive back into some of the things that we have talked about so far. One of them is the effect of barriers, okay, on wave functions. And by wave functions, I mean the wave function of a particle of interest, which is an electron. Okay, so an electron has a wave function, and it travels through space, and at some point it encounters a barrier, a potential barrier. So we've seen several barriers now. The most dramatic one, of course, is, let's say you have 0, this is minus x, this is plus x, and there's a barrier for positive x, and that barrier is, say, infinity, or it approaches an infinity. So that is a pretty tall barrier, and in that case, what we have seen is that the wave function must disappear at the onset of the barrier. That means if you have a wiggling function somewhere, it must go to 0 at that location where the barrier starts. It cannot have any amplitude. The wave function cannot have an amplitude in the barrier, okay? Because the barrier goes to infinity. The other alternative that we have seen is similar, but now the barrier is actually not finite. So the barrier has a finite, sorry, not infinite, it has a finite value. Okay, so then if you have a wiggling function on one side, it actually starting to decay in the barrier. So now there is a finite probability of finding the particle in the barrier. So these are two cases, they're very different. Case one, you will not find the particle in the barrier, and therefore the wave function must disappear to 0. The amplitude must go to 0 at the onset of the barrier. In case two, that is not so, because there you can actually find the particle in the barrier, right? So make sure you see that distinction there. Another thing that we haven't talked about is a barrier that would look something like this. This is, let's say, 0, negative x, positive x, and the barrier is now, for instance, a function of x. Okay, so this is a barrier that is not abrupt, but basically develops as a function of x. Okay, so basically it is a function of x. It's no longer a constant. It's now a function of x. And of course, in general, the barriers will be like that. In general, we will encounter barriers that actually change as a function of space. All right, so this is the case that we're going to talk about now for a very relevant situation that pertains to chemistry. So let's have a look at a barrier that changes as a function of space. Okay. So here I have a particle in green, okay, and it's going to move along x. So let's say it moves a little bit along x, but then as it does so, it will encounter a force. So this is new, because previously we haven't considered that. The particle moves in free space, there's no potential energy barrier of any kind, and therefore it doesn't experience any force. But now let's say that as the particle moves to the right, it will encounter a force that is pushing it back. Okay, so the force has the opposite sign. It pushes it to the left. So let's say it pushes the particle to the left as it moves to the right. So this is a resisting force or a restoring force. How can we write that? Well, we can write it as follows. The force equals minus kf. Kf is the force constant, or in this case, more properly called the spring constant. Okay, the spring constant. The negative sign means that it's going to act on the particle as it moves to the right, will act towards the left. So it's a force that has a direction that is counter to the propagation of the particle, right? So this is a very common force. It looks like a linear force, but you should understand the following. If the particle is moving farther and farther away from the origin, you can see that the force grows. So the force becomes stronger and stronger as the particle is moving farther and farther away. So in other words, it becomes more and more difficult for the particle to move farther away from the origin, okay? So this is called this linear restoring force, very particular case, okay? And we can now determine what is the potential well that this particle experiences, because there's of course a relation between the force and the potential. Okay, maybe you remember this from physics classes. That is basically the following. The derivative of the potential with respect to space with the negative sign is proportional to the force. Okay, so that means that the antiderivative of this expression right here is basically the potential. So if you can find the antiderivative of this expression here of F, then you know what the potential barrier function is. That's not so hard to do because the antiderivative, this is an x, linear function, so it's going to be x squared with a half in front of it, okay? So it's going to look like this. The negative sign will cancel because of the negative sign of the expression here on the right. So the negative signs cancel, and then you can very quickly determine what the potential is. You can verify that if you take the derivative of this expression right here with the negative sign, you get exactly the force, okay? So that hasn't changed. So the potential barrier that we're dealing with that describes this situation, meaning the particle experiences a force that grows and grows and grows as it moves farther and farther away from the origin. That barrier that describes that process is half times kf times x squared. Okay, so we can actually kind of draw that into the figure. This is what it looks like. This is called a harmonic well or a harmonic potential. So you can see already from the shape that if you imagine the particle moving in this well, these values here for small extensions, you see the potential is very small. In fact, at 0, it is 0. But if it moves farther and farther away, you see the potential is growing tremendously. The farther you move away, the potential grows dramatically. So it becomes more and more difficult for the particle to move into those areas, right? Okay, so let's take this potential and see if we can now solve the Schrödinger equation with this potential included. Okay, so the total Hamiltonian is this T, of course, means the kinetic energy contribution. The V now is this new V that we just talked about. So let's plug them in together. The T with the little hat, it's the kinetic energy operator, is always negative h bar squared over 2m, and then the second order derivative with respect to space. In this case, we consider a one-dimensional situation. Therefore, I only have to consider the derivative, second order derivative with respect to x. And then this new potential that now also depends on x, namely half times kf times x squared. Okay, so that is my new Hamiltonian. So what I can do now is to solve the Schrödinger equation with this Hamiltonian and see what I get. All right, so this is what I have to do. I have to solve this particular equation. That's the Schrödinger equation. This is the new Hamiltonian, kinetic energy part, potential energy part, and then, of course, times the wave function equals the energy that I'd like to find, as well as the wave function again. So this is the eigenvalue equation, the Schrödinger equation. Now, this turns out to be quite a bit of work to solve this problem. Okay, and this is not part of this course. So this is mathematics that is just one level above us in a way. Although you're invited to try to solve this problem if you want. There's well-defined methods on how to do that, but this is not going to be part of this course whatsoever. Instead, I'm going to show you what these solutions look like. Okay. So the general solution of this eigenvalue equation for the function psi are the following. Psi with an index nu, the Greek letter nu, is a function of x, equals n nu, which is a normalization constant, okay, times a function h, also is indexed with nu, and now it has a different variable y, which I will define in 2 seconds, and then times a exponential function that has y squared as its argument. So first of all, what is the y? Well, the y is defined as x, so it's proportional to x, divided by a constant, and this constant is determined by a couple of numbers that we know from the problem on the previous slide, namely h bar squared, m, that's the mass of the particle, in this case an electron, let's say, times the spring constant. And that whole thing then to the power 1/4. Okay, so that is what alpha is. Alpha is just a constant defined by the problem, depending on the mass and the spring constant. Then alpha is known, and then you know y. So y is now well defined. We don't know yet what h and n are, so let's have a look at these two things. The first thing is h. This is called the Hermite polynomial function. Okay, and here are the so-called Hermite polynomial functions. As I said, they depend on nu. So whatever the index nu is, the polynomial looks a certain way. When nu equals 0, it's very easy. The polynomial is simply 1. If it's 1, if the index is 1, then the polynomial is 2y. Then when it's 2, it's 4 times y squared minus 2, and so forth. All right? So this is a table of Hermite polynomials that you don't have to learn by heart. It's not the purpose, folks. Not at all. Just know that they exist, and if the need arises, you can always look it up in this table and plug them in the expression here. Okay? So it's just a matter of finding them in the table and then plugging it in, and then you can write out the wave function, because now you have the Hermite polynomial as a function of y. You know what y is, you know what alpha is. The only thing that we're missing here is the value for the normalization constant. So let's have a look at that. What is a normalization constant? Let's write it down. Normalization constant, function of nu, equals the following. It's a funny expression, but it's just numbers in the end. It's 2 to the power nu, and then times nu again, factorial. Okay? Then pi to the power half, so square root of pi, and then times alpha, and this whole thing is raised to the power 1/2. Okay? With a negative sign. Sorry. Important. Okay? So 1 over the square root of this whole thing is what n nu is. So in any case, you can plug in the nu's and alpha, and then you basically know what the normalization constant is for the wave functions. Okay, so here are the functional forms that are solutions of the Schrödinger equation. Don't be afraid of this. This is just finding stuff in a table and plugging it in. You don't have to do any real math. You just have to fill stuff out, basically. Okay, that's what we're asking you to do if a certain question comes up. So what does it mean? This is all good and well, but it's kind of like a bunch of numbers and a bunch of functions. I still don't have any good feel of what it is that we're looking at. So let's have a look at some pictures. Here is, again, the potential barrier, okay? This parabolic potential barrier called the harmonic well. And here you see in there the functions sketched, okay? The wave functions solutions that we just found are sketched here. The lowest value of nu is 0. So the psi with the index nu 0 is psi 0. Looks like a single bump, okay? This looks very similar to the particle in the box. The lowest wave function looks like a single half wavelength. But there is a very important distinction that you probably immediately recognize, because for the particle in the box where the walls were infinite, the wave function amplitude has to go to 0 at the edges. Here, it doesn't, because the potential does not go to 0, sorry, not go to infinity. Here, you can see it has a finite value where it's touching the barrier. So that basically means that it tunnels into the barrier, all right? So this is kind of this infamous tunneling effect that goes into the barrier, but it very quickly approaches a very small value. So the probability is very little of finding the particle beyond those locations. It's mostly confined as a kind of a bell-shaped curve within the middle of the well. Let's go to the second one. The second one looks very similar to the particle in the box. It's now a full swing, up and down, okay? So the second wave function, as it is in a particle in the box with infinite wells, has the same functional shape, but of course, there is penetration into the wall because the wall potential is finite. It's not infinite. Okay, so we go up again. The third option is, now I have 3 half wavelengths. I go to 4 half wavelengths, 5 half wavelengths, and so forth. Okay, so there's a great similarity between the wave functions of the particle in the box and this situation. However, there's differences too. Namely, in this case, I'm going to penetrate the wall, which is very different. So there's always a finite chance of finding the particle beyond these borders, so to speak. Okay, is there another difference? Yeah, the other difference is the following. The energies are spaced very differently. Okay, as you can see here, the lowest energy is half h bar omega. Now I have to explain to you what omega is. Okay, so let's first define omega and then find an expression for the energy in general. So omega here is simply related to the spring constant divided by m, and then the square root of that. Okay, so that's the definition of omega. So omega depends on the spring constant and the mass of the particle. And then the energies, which have now an index of nu, equals nu plus 1/2 times h omega. Okay, so those are the energies of these wave functions. So whenever nu, because nu, the lowest value starts at 0, okay, 1, 2, and so forth to infinity. Okay, so it starts at 0, not at 1. It's different. This is not the same as the principal quantum number n, which starts at 1. Nu starts at 0. Okay, so we put 0 in here, then the lowest energy is half h bar omega. That's the energy of the lowest wave function here. That's half h bar omega. The second one is 3/2 h bar omega, 5/2 h bar omega, and so forth. So the difference between subsequent levels, okay, let's say level the first one and the second one, is actually h bar omega. The difference between the subsequent one is also h bar omega. Okay, that is very different from the particle in the box, because the energies of the particle in the box were scaling quadratically. You remember that. Okay, so subsequent levels had a quadratic dependence in terms of energy. Here, there's a linear relation. Every consecutive level is exactly h bar omega above the previous. So the spacing between the energy levels is different from that of the particle in the box. So keep that in mind. All right, so now another thing that I can notice is the following. If I look at the spring constant here, a very high number means a very stiff spring. That means a very strong force. Okay, that means if K is very high, very strong spring constant, that means that this parabolic well is going to be very steep. Okay, so instead of it being shallow, it becomes steeper, 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 steeper. Okay, that basically means you confine the particle more. You confine the particle more, the energy separation between the states will grow. Okay, so that means you gain more quantum mechanical character. Right, so that is another manifestation of quantum mechanical character. The more you confine it, in this case, the higher the spring constant, the more these states will be separated relative to one another. All right. Another interesting thing is the following. If I look at the lowest wave function here, you see the probability of finding it in this well is highest in the middle, okay? Because, you know, the maximum is right there. So if I now look at the second one, because there's a knot here in the middle, all right? And if I now go higher, 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 and higher, you will see at some point that you accumulate more probability at the edges than in the middle. In the middle, it typically averages out to lower values than on the edges. It's not so clear here for, you know, nu equals 4. But if you go to very high numbers, let me try to sketch it for you. What you will find is you get like very high oscillations and then kind of becomes virtually flat. And then it starts to kind of oscillate like this again, like so. Okay, this is an extreme case. An extreme case. However, I like to point out that this is what you would expect if the particle approaches the so-called classical limit. So if you move up the ladder very, very high, higher energies, the well will open up. The higher you go, it becomes shallower and shallower. It goes open, okay? And that means it becomes more and more classical, more and more classical. You can see the probability of finding a particle is now highest near the edges, less in the middle, more on the edge on the other end too. That's exactly what you would expect for a classical pendulum, right? Because a pendulum moves and it has to turn around on one edge, spends more time there. spends the least amount of time in the middle, but it zips through the middle, and then on the other end, it has to turn around, so it spends more time at the turning points. That's the same here, okay? Spends more time at the turning points for states that are much higher up in energy. However, at lower energies, that is not the case. It spends more time in the middle, which is absolutely not classical, impossible in classical mechanics. So the most quantum mechanical character we find in the bottom of the well, okay, and not for higher energies where the particle starts to behave more classical. So there's a very nice transition, once again, between the quantum mechanical limit and the classical limit. That is the limit that we live in. Okay. So one more thing I'd like to point out is the lowest possible energy is once again a finite value. It's not zero. So even though nu equals zero, the index equals zero, the corresponding value of the energy is not zero. It is half times h bar omega. It's a finite value. So the 0-point energy is an actual number. That means, once again, as soon as you put a particle in this potential well, it has an energy. It must have an energy, okay? If it does not have an energy, it cannot be in there. So there's a 0-point energy, which is half times h bar omega, which is quite similar to the arguments that we were having, that we gave for the particle in the square box. Okay, so there's some other very interesting things that we can say about the particle in this harmonic well. Let's look at a couple of other examples. So in general, it looks something like this, okay? I have particle in the well, and the lowest function looks something like so, okay? So the question now is, if I take the operator x, which is a position operator, and I'm going to take the expectation value of the position operator. So basically what I'm asking is, what is the average position of my particle in the well? Now, surprisingly, if you do this, and I will not do it here, but I think this is one of the exercises on the worksheet, that turns out to be 0. All right? So the average position of the particle in this potential well actually is 0. That means, on average, it's in the middle. That's a little bit confusing, but if you think about it, not so, because basically the particle spends as much time to the left as to the right. It's completely symmetric. So that basically means, on average, it's in the middle, okay? And that's just based on a symmetry argument. Now, another thing I could do is the following. I'm going to calculate the expectation value of the square of the position operator. Now, this is not 0, turns out, okay? Very important difference, because this is not the same as the square of the expectation value. It's a very different thing, okay? I take the square of the position operator, so effectively it's a new operator, and then I'm going to determine the expectation value of it. Now, what do I find for this operation, which I believe is yet another exercise that we have to do for the worksheet? What we find is the following. It's nu plus half times h over mkf, and then the square root of that. And that turns out to be, of course, that's a definition of omega. So what I find is this, okay? So this is a value that is definitely not 0, okay? It is a value that changes. And that is important for us, because it says that if the nu is going to be a higher value, right? If nu is going to be a higher value, that means that the x squared, the expectation value of that operator, is going to be larger. What does that mean? That means if you are looking at wave functions that are of higher nu value, which means higher up the well, so to speak, okay, that explore distances farther away from the origin, that the expectation value squared looks to have more higher values. So that means that you are more likely to find the x squared position operator expectation value have higher values for the locations farther away from the origin. Okay. Now, to give you a kind of a feel for this, let's look at the operator for the potential. Okay, that will be half kf x squared with a little hat. Okay, so if I now look at the expectation value of this thing, I basically have the same expression as above. Okay, so here you have this kind of x squared and then the expectation value. This has a name. It's called the mean square displacement. The mean square displacement. Okay, that's the name of this expectation value. So the expectation value of this operator times half kf, which are just constants, but that scales with the expectation value of potential energy. So that says basically that the potential energy grows as a function of, oh, I made a mistake here somewhere. Yes, this is not correct. I was thinking about, this is not correct. Let me just take that off because that is not right. Let's just stick with this expression right here. This is correct. The kf should, in any case, it's not proportional to omega because the kf is in the wrong position. This is correct. Okay, so this is written in terms of omega because I multiply with kf and then the kf is now on top, and that means it's proportional to omega. So basically what it says that the potential energy is growing as nu is going to go to higher values. So that basically means that wave functions that have higher nu experience a higher value of the potential barrier, which makes a lot of sense, okay? Because the wave functions with higher nu experience the barrier farther away where the barrier is going to have higher values, okay? It also means that the mean square displacement, if you want to turn it in those that kind of jargon, is going to be larger. So the larger the mean square displacement, the larger the potential energy. All right. Now, we also know that the kinetic energy is the difference between the total energy minus the potential energy. Okay, we just have an expression here for the potential energy. And what is the expression for the total energy? Well, the total energy was nu plus half times h bar. And this expression here for the potential energy was half of that. Okay, so that is an easy calculation. I just simply find the following. That is the average kinetic energy. So I have now two expressions, one for the potential energy, the average potential energy, and the average kinetic energy. The kinetic energy also goes up when nu is going to go up, okay? But the interesting thing is that for all conditions, these two expressions are the same. So the potential energy and the kinetic energy, the average potential energy and the average kinetic energy, because these are expectation values, are the same for a particle that is in a harmonic well. Okay, so that's very interesting. So under all conditions, the average kinetic energy and the average potential energy of a particle in a potential well are the same. Again, this is very different from a particle in the box because a particle in the box with infinite walls does not have potential energy. Okay, it's never in the wall, but here it is. So there's a general expression of this, and that is the so-called virial theorem. And that states the following. If I have a potential that has the following shape, a times x to the power s, where a and s are real numbers, then it turns out that 2 times the expectation value of the kinetic energy operator is S times that of the potential energy operator. Now, since S equals 2 in our case, okay, because I have a square, okay, this is a square, should be 2, right? For our case, that is the potential well. That simply means that I have 2 times the kinetic energy is 2 times the potential energy. Indeed, that is the same thing we just found. Okay, these 2 things are the same. So this is a very general expression of the relation between the kinetic energy and the potential energy. All right. Now, you may wonder, why are we considering this particle in the harmonic well? What is important about it? Well, the importance is, let's consider a molecule. Okay, let's consider 2 atoms that are bonded together, and we ask ourselves, what is the kind of spring constant here? All right, and if it has a spring constant, and of course it has, then it has characteristic vibrational motion. All right, but this is still a very different case from what we considered, because these are 2 particles instead of 1. Okay, so there's like, mass A and mass B. Well, we are just dealing with an electron that is stuck in a harmonic well. These are 2 particles, Ma and Mb. So how can I reconcile this? Well, it turns out if you take the reduced mass, which you have seen before probably in your physics classes, which you can compute quite easily, as follows. Okay, so this is the reduced mass of the entire system. It turns out that the reduced mass basically behaves like an harmonic oscillator. Okay, so that means I can use this entire framework to analyze the quantum mechanical vibrations of 2 atoms that have an effective spring constant of Kf, where Kf, of course, is determined by the bond characteristics. Okay, so remember that the energies are as follows: nu times half times h times omega, h bar omega, where omega once again equals Kf over m, where m is now mu. Okay, so that basically means that I can have a prediction of the levels, the energy levels, the allowed energies that this atomic vibrator system can have, because it depends, as it says here, on the mass, the reduced mass, the effective mass of the system. Now, does this actually compute? I mean, is this actually a real thing? So let's have a look at what we would expect. Let's say if the average mass or the reduced mass goes up. So if you take heavier atoms that are vibrating relative to one another, that means that this mu goes up. If the mu goes up, that means that this omega goes down. Okay, so that means I expect lower energies for heavier systems, for heavier diatomic systems. And I expect higher energies for lighter diatomic systems. Okay, so let's have a look then at some examples, because you can actually take vibrational spectra and then see what happens. So, oops. Here is a Raman spectrum of several molecules. Okay, so one of the interesting one is H2. H2, of course, is the lightest diatomic molecule. So we expect a pretty high energy of the vibration, of the molecular vibration. And indeed, it has the highest possible vibrational energy of any diatomic. If we now look at N2, which is, of course, much heavier, we see that the energies are indeed lower, and O2 has even lower vibrational energies, as you can see. So this is a really nice scaling that has to do with the scaling in terms of the reduced mass of these molecular systems. So these molecular systems actually behave like harmonic oscillators, but not just any harmonic oscillator. They behave like quantum oscillators. And the states of these vibrational motions can be determined with the framework we just developed. Okay, so that's quite powerful. So if you are analyzing vibrational spectra, you can actually rationalize the locations of these vibrations based on the framework we just talked about. Okay. Now, for the last part here, I'd like to introduce kind of like a new form of notation, because we have encountered so far quite a few integrals of wave functions. Okay, so we're looking for a way to make those integrals look a little cleaner and perhaps easier to work with. So let's consider the following integral. So I have here an eigenfunction of some sort of operator. I call it phi, and that is being multiplied with a general function, a general wave function, psi of x. We have seen integrals like this before. Now, we can summarize this entire thing in this new notation, which looks like so. Okay, so this is basically the same integral written shorthand. Okay, now this thing has a name. This side is called the bra, and this side is called the cat. So this is called the bracket notation. Bracket notation. Okay, the bracket notation. It's very odd at first. Most students who see this are like, no way, I don't want to know anything about this. But it turns out it's actually very useful and very convenient. So the more we are meandering into this quantum mechanical landscape, the easier it will be to translate integrals of this kind in terms of the bracket notation. Okay, so let's have a look at a couple of examples of integrals that are relevant to us. So let's write down the same kind of integral, but now with an index n prime for this eigenfunction. And I'm going to multiply that by phi n. Okay, so this is basically the overlap integral of two eigenfunctions from a set, where the set is basically all the functions phi n. All right, so if I do this integral, I can write this in bracket notation very simply, short, as follows. The answer I know, that is, it's a Kronecker delta, right? We have seen this before. So this is very convenient. This is a very short way of writing the integral and its solution. Now we can also write integrals in the following way. Remember, this is a general wave function. And a general wave function I can always express in terms of a summation over the eigenstates of an operator, the eigenstates phi, let's say. So if I have this as my wave function, I can write it as follows, a summation over the eigenstates phi, where I now write everything in terms of this cat notation. Okay? So this is a little bit odd. What does that mean? Because this whole thing is defined as rewriting the integral. But now I'm writing just a single function, which is not an integral. Okay, so how do I think about this? Well, for now, we just consider this to be a regular function. And only if I multiply it from the left with a bra, it becomes an integral. Okay, so let me give you an example of that. For instance, I can calculate the following integral that I have on top. Oops. The integral that I have on top. Okay, this one. So let's write it now in the bracket notation. Looks like so, right? But now I'm going to substitute the expression right above it into this equation. And what I find is the summation over n, Cn, and then this integral again, now in the bracket notation. Okay, and I know that that is going to be the Kronecker delta is the solution to this. Okay, so what I find is Kronecker delta, and that basically gives Cn prime. because that's the only surviving term in the sum because of the Kronecker delta. Okay, so this is a much nicer way to write that integral. You don't have to write out the integral sign. You don't have to do the integration limits and so forth. You just write down the bracket notation, and you just make use of what you know about these complete sets. When they disappear, when they are orthonormal, and so forth. Okay, let me give you a couple of more examples. So let's consider the following expectation value of a general operator using wave functions that are normalized in this case. Okay, so that is the expectation value. You can call A, expectation value of operator A. This now becomes the following. Okay, so basically you see the brackets here, okay, that we used previously for the expectation values are basically the brackets here of the bracket notation, right? So you can very nicely see that the operator is sandwiched on the left with the bra and on the right by the cat. So I can also write an integral as follows. Let's say I sandwich now my operator between different functions, one phi and the other one, the general wave function again. Again, the bracket notation is a little clearer on what is going to happen to this operator. You see that? So basically it's multiplied from the left with phi, and from the right it's multiplied by psi. Okay, so now another interesting question is if I have, let's say, this integral, all right? And now I'm going to take the complex conjugate of this whole thing. What do I get? Well, you get something very nice. Let's first write it out just to make sure that we understand what we're doing. So this is the original integral. I'm going to take the complex conjugate of the whole thing. That basically means that I'm changing positions, okay? And the star of phi disappears while psi acquires the star or the asterisk, right? So this is the result, but this is actually, I can write in the new notation as follows. All right, so that is a very nice relationship because basically what I do here is that, okay? So if you take the complex conjugate, the bra and the cat basically change positions. It's a very nice and clean way of writing such integrals and such relations. All right. Now, one more thing then, and that is the following. If I have the following integral, which I now write only, well, for starters, in the bracket notation. And if I now take the complex conjugate of this thing, then what do I find? Okay, so now what we're doing is basically the following. I have A times psi dx, okay? And so what I'm doing, and now I'm going to isolate this part, all right? And then, oops, I'm going to take the complex conjugate. And what happens is this thing here is going to move to that position and acquires a star. Okay, so what I find is the operator times psi with the star, and this phi moves towards the right and loses its asterisk. So that is the operation. Okay, and what I'm going to do now is the following. This thing here, I'm going to redefine. Okay, I'm going to redefine it as I'm going to redefine it as this asterisk complex conjugate of psi, and then times A, and I'm going to add a symbol to it, this little dagger sign. Okay, that is what is written above. And then I'm going to complete the integral as follows. Okay, so this is kind of a new notation. What basically happens is if I take the complex conjugate, I'm going to switch positions of A and psi. Psi goes to the left, acquires an asterisk, and then the A, operator A, moves to the right and acquires not an asterisk, but a little dagger symbol. Okay, so that is what happens if you take the complex conjugate of an operator operating on a wave function. Okay, so the final result is the following. Okay, so that is the effect of taking a complex conjugate of this expression here above. The result that I find is kind of similar to what I find before, because the psi and the phi have changed positions, but now this A has acquired a dagger symbol. Now that has a name, and that's called the Hermitian conjugate, the Hermitian conjugate. That is the name. Hermitian conjugate, if it has a dagger symbol. Okay, so we will see more about this notation as we move along in the course. But basically, the Hermitian conjugate is defined through this operation that you see on this slide. That is the definition of taking the Hermitian conjugate of an operator. Okay? Again, we will get used to this as we go along, but this is by means of introduction of what this notation means and what it means to take complex conjugates of integrals of this kind. All right, we're 2 minutes over time, so I think it's time to call it quits for today. All right, there's a couple of questions. There's too many to to go through. All right. Are there any questions? Are there any live questions at this point?
Yeah. To bounce back on one of the questions in the chat, what happened to the asterisk symbol as you put the in bracket notation?
Yeah. So this asterisk, right, is basically this thing right here. I mean, this, you can see this is the bra has a little point. It's pointing towards the left, and that means that this wave function has an asterisk. Okay, so it doesn't disappear. It's a definition of what a bra is. Does that make sense?
Yeah. Okay. Thank you.